So far we have seen with some detail how quicksort and in particular its partition function work. In the remainder of this session we are going to be seeing the computational cost of quicksort and run it a few times, improve it a little bit, and finally say something about the complexity of the sorting problem. Remember that the complexity of a problem is the fastest algorithm complexity of any algorithm that solves the problem. So as we have already seen, n squared algorithms for sorting, and as you will see in a second, quicksort is n log n, maybe, and that's the last complexity class that we will be seeing in this course. We will think about what the complexity of the sorting problem is. Okay, here about the complexity of quicksort, about this n log n maybe thing. What's the complexity of quicksort? Well, we have it here, for example, and on one side we have the calls to quicksort, the recursive calls, which we will deal with in a second, and then we have partition. The first important thing to see is that partition is linear. As you might remember, have understood from the previous explanation, I start with left and right at the extremes of the list and I move them one position at a time until they meet. Okay, so basically, although this is a little bit convoluted, no matter exactly what branch I get into every time, I end up visiting each element in the list exactly once. Okay, so if I end up visiting each element of the list exactly once, partition is linear, is O of n. Okay, so then I have something inside of my call that's linear, and then I have a number of calls governed by these two recursive calls. If you remember from merge sort, again, 2 short videos ago, we saw that the recursive calls in the case of quicksort were built by dividing the list by half at each point. So I ended up with a recursion tree that started with a list of length n, and at each level of these recursion trees I had many lists of half the length than in the previous level until I reached level 1. As we saw for binary exponentiation, if you have something that, let's look at it from the other side, starts at 1 and then grows doubling, because if I half when I go down, I double when I go up until it reaches n, then the height of the tree is k, and because I have doubled every time, the number at the top of the tree is 2 to the k, and 2 to the k is n. So again, k is log n. So if I was lucky and quicksort divided my two lists in exactly equal parts, if I had chosen a pivot that was exactly in the middle of the list every time, I would have the same result. I would have lists of length half every time at the total height of the tree. That's that's log n. Okay, then I would have something that's n called n because of the partition, something that's linear because of the partition called log n times, and I would have a total of an n log n algorithm. Okay, see, I have solved the complexity for merge sort there basically, but you can go check it out too. The thing is that sometimes I might not be that lucky. Okay, so the best possible complexity is n log n because of this logarithmic height of the tree if I divide every time the data into equal halves. Okay, what happens if I'm not happy? If I'm not lucky? Well, if I'm not lucky, I might end up with each recursive call, dividing my two halves of the quicksort call, sorry, I'm lost here, with these two calls being one of them with all the elements except one, except the pivot, and the other one being empty. If I choose as my pivot the smallest element, the list that contains the elements that are smaller than it will be void. So if I'm unlucky, I end up with a list with one single call with length of its list n minus 1. And if that happens every time, my recursive tree only decreases by 1 at each level, and I end up with a single branch of length n. If I'm that unlucky, if I have n levels, very small levels, but levels still in my recursion tree, and in each of them I spend n, then the worst case complexity of my quicksort algorithm would be n to the squared. Okay. So I have an algorithm that's sometimes, maybe, if I'm lucky, n log n. And sometimes, if I'm not lucky, it can be up to n squared. And that happens with some pivot selection strategies. Okay, we did it random, but with some pivot selection strategies and some data inputs, this might actually happen. So, is it worth using quicksort? Well, I'm not going to go very deep into this, and you can look into the average case complexity of quicksort, but the short answer is that yes. Basically, by randomizing part of it, as we did by choosing a random pivot, you make the extremely unlucky case very, very unlikely. And in practice, with normal data, it doesn't usually happen. So this is a pretty simple algorithm to code, with this and the partition up there, that works well most of the time. It might have some bad cases, but usually it works pretty fast. So usually, yes, it is worth using. Okay, let's run the code a little bit more again. And let's add again the function to compute random lists. And let's see a few executions of our quicksort algorithm, and let's see how long it does take to run. When I say that usually it works well, what do I really mean in terms of running time? Here I have a nice loop where I'm just generating lots of random integer lists and checking whether or not the output that I get is the same as a sorted built-in function in Python. So basically I'm comparing to the output of an algorithm called P2Sort, of which I will say a bit more in a second. So basically this amounts to checking many times whether or not, 100 times in this case, quicksort works well, sorts correctly, and it does. I can even improve it to make it a little faster. For example, one thing that is used in real applications is that for small lists, it doesn't really matter what sorting algorithm you use. But if you're making lots of recursive calls on the lower levels of the recursive call tree, then that might actually amount to some, let's say, wasted time. So a compromise is reached by using some other sorting algorithm. In this case, we will use insertion sort because we have it from a previous session for small instances of quicksort. So I have modified my code very slightly so that if the length of the list that I'm sorting is smaller than a threshold that I'm going to set at 10 by default, this is default parameter declaration in Python. Again, we saw this a while back. So if I'm under 10 or I'm under any other threshold that I have given for the length of my list, I will call insertion sort. And to the squared, not very efficient, but for small lists, it's okay. And with this, I'm getting rid of the whole lower part of my recursive calls tree, which might be actually pretty big. And then if I'm not within this threshold, I call quicksort. I do the partition and I do the two recursive calls. So hoping that this will make it a little bit faster, and let's see its running time. Let's run it a few times and let's see the time. Okay, this is pretty small. I'm running it to sizes of 5,000, so quite a lot. Again, when I plot running times, neither the shape nor the value are very informative, but they help me make some comparisons. For example, let's compare the running time of quicksort versus the running time of insertion sort. Okay, here it is. Again, similar shape as before for both, but when I plot them together, whoa, I see that quicksort is much faster than insertion sort. Okay, so even though part of it is actually insertion sort, by doing these recursive calls, divide and conquer strategy, I get a much faster algorithm. Okay, so hope I have convinced you that even though quicksort has a pretty nasty worst case behavior, in general it does behave pretty well. Am I done? Is this the fastest sorting algorithm that I will ever see? Well, no. Especially if you go specific enough, you're always going to see many more sorting algorithms that can be faster. Let me compare quicksort to teamsort, this built-in Python sorting algorithm, and I will see that quicksort was fast. Teamsort is also fast, and when I compared the two of them, I realized that teamsort is much faster than quicksort. This tendency is a little bit more. You can see the growing a little bit more. So perhaps the let me make this a little bit bigger. Maybe I will be able to see it a little bit prettier. Basically, I can see that teamsort is a faster algorithm, but I see the growth of it a little bit here. Okay. Yes, this is similar. I see the separation much better here when I have bigger data, and I see some growth in the teamsort algorithm, but quicksort grows much faster. Okay. Teamsort, you can check it up. I recommend that you do. Is an algorithm that uses merge sort and that tries to take advantage of parts of the list that are already sorted and just breathe through those. Okay. So in part it's merge sort for short sizes. I think it also uses insertion sort, and in some other it makes clever skips of parts that it realizes are already sorted. So I have seen an algorithm that's n log n if I'm lucky. Actually, to remember merge sort, but I have seen all the details with quicksort, and I have seen that it's not the fastest algorithm that I can think about. Teamsort itself is faster. What's the complexity of the sorting problem? Is there something that's going to be ever faster than teamsort? Well, that's a very good question, and I encourage you to go and check it out. And if you're ever working in an application where the sorting of your data is really important, you will see that there are many dedicated algorithms for particular types of data. Today, as we are speaking in general terms, okay, the complexity of the sorting problem is n log n. So teamsort for most application is going to be the best that I can do, probably. Okay. There are some sorting algorithms, for example, two come to mind, radix sort and bucket sort, that claim that they are O of n. Okay. So they claim to be faster than the n log n, for example, teamsort algorithm. And if that is true, then the complexity of the sorting problem would not be n log n, but it would be n. But the thing is that these two algorithms only work under certain circumstances. For example, bucket sort relies heavily in using hash functions. Okay, bucket sort is a very simple algorithm. You can check it out. And it relies on the fact that these hash functions, which, if you remember, are also the basis of dictionaries, these hash functions are supposed to distribute the data evenly. So in the same way that we used to say that data access in a dictionary is constant if the dictionary works well, we could say that bucket sort is linear if the hash function, the dictionaries under it, work well. That happens for lots of data and bucket sort is used, but it doesn't happen for all data all the time. So I would not say that the general formulation of the sorting problem is n, but I would say that it's n log n. And if you want some more detail, you can see the discussion that I listed here. Okay, so that's it for this session, and that's it for this course. Thanks for listening, and I hope you enjoyed it. Go back to the notebooks, play with the code. If you have any questions, just drop me an email. See you again in the next course that will deal with object-oriented programming. Thank you for listening.